somewhere out beyond the orbit of Jupiter, moving fast enough to escape the sun's gravity forever. There is a visitor. It did not form here. It does not belong here. And until a few months ago, nothing like it had ever been seen this clearly. Its name is a string of letters and numbers that sounds more like a serial code than a celestial object. 3I/Atlas. The I stands for interstellar. The 3 tells you something remarkable all by itself. This is only the third object ever confirmed to have come from outside our solar system. Not the third comet. Not the third asteroid. The third object, period, in the entire recorded history of astronomy, that we can say with confidence was born around another star, in another system, long before our sun even existed. And now, the James Webb Space Telescope has turned its enormous gold-plated eye toward it. What it found is rewriting what scientists thought they understood. Not just about this one object, but about the chemistry of the galaxy itself. This is the story of 3I/Atlas, and the strange, beautiful puzzle James Webb just handed us. Let's set the scene. For most of human history, we assumed comets and asteroids were local. Leftover debris from the formation of our own solar system, orbiting the sun in long ellipses, occasionally swinging close enough for us to see a tail. Predictable. Familiar. Then, in 2017, something broke that assumption. An object called Oumuamua shot through the inner solar system on a trajectory that made no sense for anything born here. It was moving too fast on a path too straight to ever have been gravitationally bound to the sun. It came from interstellar space, swung past us in a matter of weeks, and left. Astronomers barely had time to point telescopes at it before it was gone, tumbling out into the dark, leaving behind more questions than answers, including a strange acceleration that some scientists still can't fully explain. 2 years later, a second interstellar visitor arrived, Comet 2I/Borisov. This one behaved more like a normal comet with a visible tail of gas and dust, giving astronomers a clearer look at interstellar chemistry for the first time. It was reassuring, in a way, evidence that other stars do produce comets similar to our own. Now there is a third, and 3I/Atlas may be the most important one yet, for a simple reason: timing. Unlike its predecessors, astronomers spotted this object early, while it was still far from the sun, which means we have had time to prepare. Time to point the most powerful telescope ever built directly at it before it reaches its closest approach. Time to actually study it instead of just watching it vanish. Discovered by the Atlas Survey, the Asteroid Terrestrial Impact Last Alert System, a network of telescopes designed to scan the sky for anything dangerous and unexpected, 3I/Atlas was flagged almost immediately as something unusual. Its trajectory was hyperbolic, meaning it is not in orbit around the sun at all. It is simply passing through, a one-time guest, following a path that will take it back out into the galaxy and never return. Calculations suggest it has been traveling for an extraordinarily long time, potentially billions of years, drifting between the stars long before it ever entered our field of view. Some researchers estimate it could be older than the solar system itself. If that holds up, 3I/Atlas isn't just a visitor. It's a time capsule, a frozen fragment of another planetary system, formed around a star we may never identify, sealed in ice and dust, and now, for a few fleeting months, within reach of our instruments. That is what makes the James Webb observations so significant. Webb wasn't built to look at planets the way Hubble was. It was built to look at chemistry. Its instruments are tuned to infrared light, the kind of light that reveals the molecular fingerprints of gas and dust, what something is actually made of, not just what it looks like. When astronomers pointed Webb at 3I/Atlas, they weren't hoping for a prettier picture. They were hoping to read its composition like a chemical signature, written in light. And what came back surprised almost everyone. The first thing Webb measured was the coma, the cloud of gas and dust that surrounds a comet's icy nucleus as it warms in sunlight. Comets are essentially dirty snowballs. Ice, frozen gases, and dust, all bound together since the early days of planetary formation. As they approach a star, the ice begins to vaporize, releasing gas that forms a glowing halo, and sometimes a tail. By analyzing exactly which gases are present, and in what ratios, scientists can work out what kind of environment the object originally formed in. In our own solar system, comets typically show a fairly consistent mix. Water ice dominates, with carbon dioxide and carbon monoxide present in smaller, fairly predictable amounts. It's a chemical baseline built from studying thousands of comets over decades. 3I/Atlas broke that baseline. Webb spectroscopy revealed an unusually high ratio of carbon dioxide to water, far higher than what we typically see in comets from our own solar system. In some readings, carbon dioxide appeared to be the dominant gas being released, rather than water, which is highly unusual. For context, imagine examining ice cores from different parts of the world and finding one that's chemically nothing like the others. Not contaminated, not damaged, just fundamentally formed under different conditions. That's roughly the level of surprise this caused among cometary scientists. Why does that matter? Because the ratio of carbon dioxide to water in a comet is thought to reflect the temperature and conditions of the disk of gas and dust it formed in billions of years ago around its parent star. A high CO2 to water ratio suggests 3I/Atlas may have formed farther from its star, in a colder region of its system, where carbon dioxide ice could condense more easily, or that the chemistry of the disk itself was different from what shaped our own solar system's comets. In other words, Webb isn't just telling us what 3I/Atlas is made of. It's giving us a glimpse into the conditions of an entirely different planetary nursery, light years from here, that existed and possibly stopped existing long before Earth had oceans. Then there's the nickel. This one raised eyebrows even among scientists who study comets for a living. Spectroscopic analysis picked up a trace signature consistent with nickel vapor in the coma, a detail eerily reminiscent of a phenomenon seen in a small number of solar system comets, where nickel and iron compounds sublimate even at relatively low temperatures, far from the sun, in a process scientists are still working to fully understand. Finding that signature in an interstellar object is significant for two reasons. First, it suggests 3I/Atlas shares at least some chemical processes with comets that formed right here, around our own sun, hinting that certain rules of comet chemistry might be more universal than we assumed. Second, it raises a genuinely open question. What kind of geological or chemical history produces detectable metal vapor in an object that has spent most of its existence in the deep cold of interstellar space, far from any star's warmth? There's also the matter of deuterium, a heavier isotope of hydrogen, sometimes called heavy hydrogen. The ratio of deuterium to regular hydrogen in water ice is a kind of cosmic thermometer. It tells you something about where and under what conditions that ice originally formed. Early measurements have suggested 3I/Atlas's water carries a deuterium signature that differs from typical solar system comets, which would again point to formation in a different chemical environment altogether. Another star, another disk, another set of rules. Stack all of that together, the carbon dioxide excess, the nickel signature, the deuterium anomaly, and you start to understand why 3I/Atlas has become one of the most closely watched objects in the sky. It's not behaving like a textbook comet. It's behaving like a comet from somewhere else, built from different ingredients, shaped by a different star's particular chemistry, frozen in time, and now passing within reach of our most sophisticated instruments for a few brief months. It's worth pausing here to appreciate exactly how astonishing it is that we can even ask these questions. 3I/Atlas is small, likely just a few kilometers across, maybe even smaller depending on how reflective its surface is, and it is currently hundreds of millions of kilometers away, moving at tens of kilometers per second relative to the sun. And yet, by capturing the faint infrared light scattered and emitted from its tiny halo of gas, scientists can determine its chemical composition with enough precision to compare isotope ratios. That's not just impressive engineering. That's one of the great triumphs of modern astrophysics, the ability to read the chemical history of an object that formed around another star without ever sending a spacecraft anywhere near it. Of course, with any genuinely strange result, scientists do what scientists are supposed to do: question it. Some researchers have pointed out that comets can behave inconsistently as they warm up, venting different gases at different rates depending on how the heat penetrates their surface. It's possible that what Webb captured is a snapshot of an unusual but temporary outgassing event, rather than a permanent signature of the object's bulk composition. As 3I/Atlas continues its journey closer to the Sun, astronomers expect its activity to increase, which should provide more data and more opportunities to either confirm or revise these early findings. There has also been healthy scientific debate about exactly how much carbon dioxide is being detected versus how it's being interpreted, since separating the comet's true composition from instrumental and observational effects is genuinely difficult work. This is, in many ways, the most exciting part of real science. Not a single dramatic announcement, but a careful, ongoing process of measurement, remeasurement, and refinement playing out across observatories around the world in close to real time. And it's exactly that real-time quality which makes 3I/Atlas so compelling. We are not reading about this in a textbook years after the fact. We are watching the data arrive. Teams of scientists are comparing notes across continents, refining models, occasionally disagreeing, and slowly converging in front of us, on a more complete picture of an object that began its journey before our own planet had life on it. Because here's the truly staggering scale of this story. Based on its trajectory and velocity, some estimates suggest 3I/Atlas may have been traveling through interstellar space for several billion years. Not centuries, not millennia, billions of years. If that's accurate, this object began its journey before the Earth had an atmosphere capable of supporting life as we know it. It may have formed around a star that no longer exists in the form it once did. It may have drifted past stars that have themselves since died, exploded, or faded into white dwarfs. Through all of that, through the entire span of life evolving on Earth, through the rise and fall of everything we call human history, this small, icy fragment was simply drifting. Silent, cold, patient. And now, for a few months, it happens to be passing close enough for us to look at it properly. There's something almost poetic about that. Of all the trajectories it could have taken, of all the billions of years it has spent crossing the empty space between stars, it happens to pass near our small, blue 3.5-billion-year-old planet at the exact moment in history when a species capable of building space telescopes exists to notice. A few thousand years earlier, and we'd have had no instruments capable of detecting it at all. A few thousand years later, and who knows what we'd have built instead. The timing, statistically, is almost absurd, a reminder of just how much of scientific discovery depends not just on capability, but on simply being in the right place, looking in the right direction at the right moment. It's also worth addressing something that tends to follow stories like this one: speculation about artificial origin. Whenever an interstellar object behaves in ways that don't perfectly match our existing models, whether it's Oumuamua's strange acceleration or 3I/Atlas's unusual chemistry, there is a natural human instinct to wonder whether we might be looking at something built, rather than something that simply formed. It's a compelling idea, and to be fair, serious scientists have raised it as a hypothesis worth not dismissing outright, simply because rigorous science means not assuming the answer before you've gathered the evidence. But it's important to be clear about where the actual data points. Every measurement collected so far, the trajectory, the outgassing behavior, the spectroscopic signatures, is consistent with a natural icy body, behaving the way a comet behaves when it's heated by a star, just with a chemical composition shaped by a different, unfamiliar environment. Unusual does not mean impossible. It means we are looking at something that simply didn't form here, governed by conditions we don't yet fully understand. The far more likely and frankly more remarkable explanation isn't that we've encountered an artifact. It's that we've encountered nature doing what nature does, just somewhere else under different rules, and we are privileged enough to be watching it happen. In a way, that's a far more profound story than the speculative one. Because what 3I/Atlas represents, beneath all the anomalies and open questions, is direct physical evidence that the universe is, in fact, more chemically diverse than we assumed. For decades, our entire understanding of how comets and planetary systems form was built on a sample size of exactly one solar system, ours. We extrapolated rules from a single data point and assumed, reasonably, that those rules were close to universal. 3I/Atlas is quietly suggesting otherwise. It's a second, really a third, counting Borisov, independent data point, formed under entirely different conditions, and it does not perfectly match our model. That's not a failure of science. That's science working exactly as intended. A theory gets tested against new evidence, and when the evidence doesn't fit, the theory gets refined. Every interstellar object we've now studied, Oumuamua's strange shape and acceleration, Borisov's surprisingly carbon monoxide-rich coma, and now 3I/Atlas's carbon dioxide excess and unusual isotope signatures, has nudged our models a little further from comets are basically all the same towards something closer to the truth. Planetary systems across the galaxy are diverse, shaped by their local chemistry, their stars' particular characteristics, their position within their galactic neighborhood, and circumstances we are only beginning to map. There's a reason scientists describe interstellar objects as messengers. They're not just rocks and ice drifting through space. They are, in the most literal sense, samples, physical specimens of material that formed somewhere else, around some other star, under conditions we can never directly visit. We cannot send a spacecraft to another star system within a human lifetime. The distances are simply too vast, the timescales too long, even with our most ambitious propulsion concepts. But every few years, it seems the galaxy sends us a sample instead. A small frozen fragment, drifting through on its own ancient trajectory, asking nothing of us except that we look. And we are looking. As 3I/Atlas continues its journey toward and past its closest approach to the Sun, observatories around the world, ground-based telescopes, space telescopes, radar facilities, are coordinating to gather as much data as possible before it fades back into interstellar darkness. James Webb's infrared spectroscopy is just one piece of a much larger international effort. Optical telescopes are tracking its brightness and any changes in its tail. Radio observatories are searching for molecular signatures invisible to infrared instruments. Every data point adds another layer to the picture. Because here's the part that should genuinely keep you up at night, in the best possible way. Once 3I/Atlas passes by, it's gone. Forever. Unlike comets bound to our sun, which return every few years or decades or centuries on predictable orbits, 3I/Atlas is on a one-way trip. It will swing around the sun, pick up a final gravitational nudge, and head back out into interstellar space, never to return to our solar system again. Whatever data we collect during this brief window, these few months while it's close enough to study, is all the data humanity will ever have on this particular object. There is no second chance. No follow-up mission a decade from now. No, let's wait for it to come back. That's part of what makes this moment in astronomy feel different from routine observation. It's not like watching a planet we can study for centuries. It's more like catching a single, fleeting glimpse of a stranger passing through, knowing you'll likely never see them again, and trying to learn everything you possibly can in the brief time you have. So what happens next? Over the coming weeks, as 3I/Atlas approaches its closest point to the Sun, what astronomers call perihelion, its activity should increase. More ice will vaporize as it warms, releasing more gas, producing a brighter, more detectable coma and potentially a more visible tail. This increased activity is exactly what scientists are hoping for. More data, more spectral lines to analyze, more chances to refine or confirm the early, startling readings from Webb. There's also continued analysis happening on the data already collected, teams comparing notes, cross-checking instrumental calibrations, running models to better understand exactly why the carbon dioxide ratio is so unusual, and what it implies about the object's formation history. Some of the most interesting science happens not in the moment of discovery, but in the months and years afterward, as researchers slowly piece together what the data is actually telling us, layer by layer. And there is a broader significance here, too, one that extends well beyond this single object. Every interstellar visitor we successfully study makes us better prepared for the next one. Survey systems like Atlas are improving, becoming more sensitive, catching objects earlier in their approach. The techniques developed to analyze 3I/Atlas's chemistry will be refined and ready to apply more quickly the next time something like this appears. And statistically, given how many interstellar objects we now believe regularly pass through our solar system without ever being detected, there will be a next time. Scientists estimate that objects like this may pass through the inner solar system more frequently than previously assumed. We simply haven't had the survey capability to catch most of them until relatively recently. Which raises a quietly remarkable thought. 3I/Atlas is not unique because interstellar visitors are rare. It's unique because we finally have the tools to notice and the timing to study it properly. The galaxy has likely been sending us these messengers all along, drifting silently past Mars, past Jupiter, past Earth itself, completely undetected, for as long as our solar system has existed. We are simply living in the first generation of humans equipped to actually catch one, look closely and ask, what are you and where did you come from? It's worth taking a moment to consider what it actually means to hold, metaphorically, through data rather than in hand, a piece of another solar system. Every element in your body, every atom of carbon, oxygen, nitrogen was forged inside a star, most of them long dead, scattered across the galaxy by supernovae billions of years before our sun ever formed. In that sense, we are already made of interstellar material. But 3I/Atlas represents something different. Not ancient stardust recycled into new systems, but intact material from another system entirely. Ice and dust that formed somewhere else around a different star under different rules and then simply never stopped traveling until physics finally brought it close enough for us to see. Whatever specific answers come out of the ongoing analysis, whatever the final, refined ratio of carbon dioxide to water turns out to be, whatever explanation emerges for the nickel signature, whatever the deuterium measurements ultimately confirm, the larger lesson of 3I/Atlas is already clear. The universe does not run on a single template. Solar systems are not cookie-cutter copies of our own. Somewhere out there, around other stars, under other conditions, the basic ingredients of planet formation, ice, dust, gas, rock, are being assembled according to rules that are recognizably similar to ours, but meaningfully, measurably different. And every few years, almost as if by gift, a small fragment of that difference drifts close enough for us to study it directly, using nothing more than light captured by mirrors here on Earth and in orbit above it. That, more than any single anomaly or measurement, is the real story of 3I/Atlas. Not a mystery to be solved and closed, but a window brief, precious, and utterly irreplaceable into the staggering diversity of planetary systems scattered across our galaxy. A reminder that for all we've learned about our own solar system, it is just one example among what are likely billions of variations, most of which we will never see, except for the rare moments when one of their fragments happens to wander close enough to notice. 3I/Atlas will not stay. In a matter of months, it will swing past the sun, gather speed, and begin its long, silent retreat back into the space between the stars, carrying with it whatever secrets we failed to ask in time. It came from a place we will never visit, shaped by a star we may never identify, and it is headed toward a destination so distant that the concept of destination barely applies. It is simply going back to where it came from, out there, into the vast, dark, star-scattered expanse that makes up almost all of the universe we live in. And for this brief moment, while it is still close enough to listen to, the most powerful telescope humanity has ever built is doing exactly that. Reading its chemistry, measuring its isotopes, tracing the faint infrared whispers of ice turning to gas, billions of years after that ice first froze around a star none of us will ever see. We don't know everything about 3I/Atlas yet. We may never know everything, but we know more than we did a few months ago, and considerably more than we knew about any interstellar object before it. And in science, that's the entire point, not certainty but progress. Not final answers but better questions, asked with better instruments, pointed at exactly the right patch of sky, at exactly the right moment. Somewhere out there, right now, 3I/Atlas continues on its ancient trajectory, indifferent to the attention it's receiving, carrying its billion-year-old chemistry past a small blue planet that, for a few fleeting months, finally had the tools to ask it where it had been. And it answered, not in words, but in light, scattered, faint, and infinitely patient, exactly the way the universe usually speaks, if only we know how to listen.